Welcome, everyone, to a really special deep dive. We're celebrating CERN's 70th anniversary.
70 years.
That's right, 70 years of the European Organization for Nuclear Research. And how are we celebrating? We're diving deep into 7 physics milestones, really showcasing how CERN has shaped our understanding of the universe.
I think what's amazing is how each milestone kind of builds on the last one, like
Yeah,
a relay race of discovery.
totally. So let's rewind back to 1957. The year CERN's first accelerator, the Synchrocyclotron, came online. What was the goal with this machine?
Well, the Synchrocyclotron, or SC, was all about accelerating protons, giving them a ton of energy.
So these protons, those positively charged particles in an atom's nucleus, they're being whipped around faster and faster.
Yeah, like a particle racetrack, gaining energy with each lap.
Oh yeah, I'm picturing it. What happened when these high-energy protons hit their target?
Early on, the SC scored a win by measuring the decay of a particle called the pion.
Pions, they're like messengers of the strong force, right?
Yeah.
The force that holds the atom's nucleus together.
Exactly. And the SC confirmed that pions could decay into electrons and neutrinos.
Which was a big deal, I imagine.
Huge. This type of decay was predicted to be super rare, so it really showcased how sensitive the SC was.
So confirming a rare decay, that's impressive. But I heard there's another SC discovery with even broader implications. Something about the muon and its magnetic moment.
Ah, yes. The muon's anomalous magnetic moment, or G-2, a fascinating story.
G-2. Okay, break it down for me.
Let's start simple. The muon, it's like a heavier cousin of the electron.
Okay, I'm with you.
And all charged particles, they have this intrinsic property, a magnetic moment. Think of it like a tiny internal magnet.
Got it. So a spinning charged particle, it's like a mini bar magnet.
Precisely. Now, according to a theory by Dirac, if the muon was perfectly point-like, meaning no internal structure—
No subcomponents, a truly fundamental particle.
Exactly. Then, its magnetic moment would have a specific value represented by G. And Dirac's theory said G should be exactly 2.
G equals 2. Nice, clean.
Hmm.
But I'm guessing nature had other plans.
You bet. When they measured the muon's G at the SC, they found a tiny but measurable deviation from 2.
Like a tiny imperfection in a perfect diamond.
Perfect analogy. And this anomalous moment tells us that the muon isn't just a simple point.
There's more to it than meets the eye. So what does this anomaly tell us about the muon?
It tells us it's interacting with other particles, even in a vacuum.
Wait, I thought a vacuum was empty.
Not according to quantum mechanics. Empty space is actually teeming with virtual particles, popping in and out of existence.
Okay, that's mind-bending. So these virtual particles are nudging the muon's magnetic moment, causing that deviation from G equals 2.
Bingo. And by carefully measuring this anomaly, we can actually peek into the muon's interactions with these virtual particles, which in turn tells us about the fundamental forces at work.
So measuring a seemingly obscure property gives us insights into the fundamental nature of reality itself.
You got it. And the team at the SC, led by Leon Lederman, they nailed the muon's G-2 measurement. First to 2% accuracy, then they refined it to 0.4%.
Those are tiny numbers.
And those tiny numbers confirmed that the muon behaves as quantum mechanics predicts.
Validating quantum mechanics, that's huge.
It was. And this story's not over. Fast forward to today, and researchers at Fermilab are chasing the muon's G-2 with even more precision.
So they're continuing this legacy.
They are, and their latest findings, well, they hint at a possible discrepancy with the standard model.
Ooh, a discrepancy.
Yeah.
That sounds like trouble for our current understanding.
Maybe. It could be new particles, new forces, something beyond what we know, or maybe just a subtle effect we haven't accounted for yet. It's too early to say, but it's sparked a lot of excitement.
Wow. From validating the standard model to maybe hinting at its limits, the synchrocyclotron's legacy lives on. But let's shift gears now. Our next milestone features a giant bubble chamber, Gargamelle, and another fundamental force, the weak force.
Gargamelle, a true behemoth, and the weak force, responsible for things like radioactive decay.
Okay, Gargamelle, a giant tank filled with liquid, hit by a beam of neutrinos, those ghostly particles. How do you even catch those?
That's the beauty of the bubble chamber. When a charged particle zips through the superheated liquid in Gargamelle, it leaves a trail of tiny bubbles.
Like a tiny vapor trail, revealing its path.
Exactly. And these trails are photographed, analyzed, and from there, we reconstruct the particle's path and interactions.
So Gargamelle was a giant neutrino camera. What were they hoping to learn about the weak force from these neutrino interactions?
Well, there was this theory called the VA theory, which explained some aspects of the weak force, like parity violation. but it had some inconsistencies.
Ah, inconsistencies. The telltale sign that there's more to the story. What happened next?
Along came the electroweak theory, developed by Glashow, Salam, and Weinberg. They proposed a new particle, the Z boson, which would mediate a new type of weak interaction called weak neutral currents.
New particle, new interaction. This is getting complex.
It is, but stay with me. So the hunt was on for evidence of these weak neutral currents, and Gargamelle was leading the charge.
I can imagine sifting through thousands of images, searching for a specific interaction.
It was a monumental effort. But eventually, a postgraduate student, Franz Joseph Hessert, spotted a unique electron event. It could only be explained by the exchange of a Z boson.
A postgraduate student making a discovery that changes physics.
Incredible. What happened next?
They knew they had something big, but they were meticulous. They double-checked, triple-checked their analysis, ruled out every other possibility.
Yeah.
And the scientific community, at first, they were skeptical. But the evidence was undeniable.
So the observation of weak neutral currents in Gargamelle became a cornerstone of the electroweak theory.
It did. And it paved the way for the later discovery of the W and Z bosons themselves.
From a pioneering accelerator to a giant bubble chamber, CERN was making waves.
Absolutely. And this is just the tip of the iceberg. CERN's story is filled with remarkable discoveries and incredible technology.
All right, let's keep this momentum going. We've talked about theoretical predictions and hints, but now we're diving into confirmed discoveries, right? What's next on our CERN adventure? Next up, we're exploring CERN's super proton synchrotron, the SPS, and its role in observing the W and Z bosons, those elusive particles that mediate the weak force.
Buckle up, everyone. It's about to get even more fascinating.
By the late 1970s, the electroweak theory was gaining serious traction, but there was a problem. The W and Z bosons, those particles responsible for the weak force, they were still missing in action.
So the theory was sound, but the stars of the show were playing hard to get. Must have been frustrating.
It was a challenge that demanded a new level of ingenuity. You see, the W and Z bosons were simply too massive to be produced by any collider at the time.
Like heavyweights needing a bigger ring, a more powerful arena. What did CERN do?
They turned to the super proton synchrotron, the SPS. It was originally designed for fixed-target experiments, but they ingeniously repurposed it into a proton-antiproton collider.
Wait, antiprotons, antimatter. How do you even wrangle enough antimatter to smash into protons? It sounds like science fiction.
It does, right. But thanks to Simon van der Meer and his groundbreaking technique, stochastic cooling, it became reality.
Stochastic cooling. That sounds intense.
Think of it like taming a swarm of bees, gathering them into a focused beam. That's what stochastic cooling did for antiprotons.
So they had their souped-up accelerator and their beam of antiprotons. But to actually catch these W and Z bosons, they needed detectors, right? Special ones.
Two massive detectors, UA1 and UA2, were built specifically for this task. UA1 was truly remarkable, with a gigantic dipole magnet, a central tracker with high-resolution drift chambers, and a cutting-edge calorimeter.
All designed to capture the energy of particles.
Precisely. It was like a giant, multi-layered trap designed to snare those bosons and reveal their secrets.
Sounds impressive. What about UA2? Did it have a different role?
UA2 focused on electron detection. See, a key signature of the W boson decay is the production of an electron. UA2 was designed to catch those electrons with its simpler, full-coverage calorimeter.
So two detectors, each with its own strengths, working together. A clever approach.
It was. And both teams strategically focused on a specific decay of the W boson, the one into an electron and a neutrino.
Why that specific decay?
Because it provided a clear signal amidst all the chaos of the collisions, like a beacon shining through the fog.
So they were looking for a very specific pattern, a signature that screamed W boson. Did they find it?
They did. In January 1983, both UA1 and UA2 independently announced the discovery of the W boson.
That must have been a huge moment.
It was a monumental achievement, confirming a core prediction of the electroweak theory. A huge step forward in understanding the weak force.
W boson, check. What about the Z boson? Did they find his partner in crime too?
It took a bit longer as the Z boson is produced less frequently. But as the data from both experiments piled up, the evidence for the Z boson became clear.
Another win for the electroweak theory.
Absolutely. It was a testament to the power of international collaboration and the dedication of hundreds of scientists from around the world.
A global effort leading to a major discovery. And didn't this discovery earn someone a Nobel Prize?
It did. Carlo Rubbia and Simon van der Meer shared the Nobel Prize in Physics in 1984. Rabi'a for leading UA1, and Vandermeer for his ingenious stochastic cooling, which made those intense antiproton beams possible.
The perfect blend of theoretical insight and technological innovation. So after such monumental discoveries, what was next for CERN? Did they take a break?
Not a chance. The discovery of the W and Z bosons wasn't the end. It was the start of a new era, the precision era. And that's where our next chapter takes us. The Large Electron-Positron Collider, LEP.
LEP, from protons and antiprotons to electrons and positrons.
Yeah.
Always pushing the boundaries.
What made the LEP era so special?
LEP was all about precision. It wasn't just discovering new particles. It was about meticulously measuring the properties of the known ones, testing the standard model with incredible accuracy.
Like going from a rough sketch to a high-definition image. So what were some of the highlights of the LEP era?
One of the early wins involved measuring something called the Z-line shape. Basically, it's plotting the probability of producing a Z boson as you vary the collision energy. So like finding the sweet spot where Z bosons are most likely to pop up.
Precisely. And the shape of this line tells us a lot about the Z boson. For instance, it can decay into various particles, some visible, some invisible.
Invisible particles, like neutrinos, always sneaking around.
Exactly. By carefully analyzing the Z-line shape, they could deduce the number of those invisible decay channels, which tells us how many types of light neutrinos exist.
So what did LEP reveal about these neutrino families?
The data conclusively showed that there are 3 and only 3 light neutrino families, a major confirmation of the standard model.
3. Got it. So LEP wasn't just about discovery, it was about confirming and refining our understanding. And you mentioned precision. How did they achieve such accuracy in their measurements?
It required extraordinary control over the beam energy and luminosity, which measures the rate of collisions. They used a clever technique called resonant depolarization to measure the beam energy with mind-blowing accuracy.
Mind-blowing how?
They could measure the beam energy so precisely that even the moon's gravity played a role. Talk about attention to detail.
Wow. That's some serious precision.
Yeah.
What about luminosity? How do they measure that so accurately?
They used a process called Paba scattering, where electrons and positrons scatter off each other. The challenge was measuring these scattering events at very small angles, requiring super precise alignment of the detectors and precise knowledge of their geometry.
So basically hitting a bullseye from miles away. From confirming the standard model to setting the stage for future discoveries, the LEP era was truly remarkable. But I'm sensing there's even more to CERN's story.
Oh, there's much more. From the mysteries of antimatter to recreating the conditions of the early universe, CERN has been at the forefront of some mind-boggling science.
Okay, let's dive into the world of antimatter. Because let's be honest, antimatter sounds like something straight out of Star Trek.
It does, doesn't it? But it's very real, and CERN has played a leading role in understanding it. One of the big questions is why our universe is made mostly of matter. Shouldn't matter and antimatter have been created in equal amounts during the Big Bang and just annihilated each other?
That's a great question. It's like the universe decided to pick a favorite. How has CERN helped us understand this?
CERN has been a pioneer in antimatter research. Back in 1965, they made a breakthrough by creating the first complex antimatter system, the antideuteron. It wasn't just an antiproton, it was an antinucleus, made of an antiproton and an antineutron.
So not just the antimatter version of a proton, but the antimatter version of a nucleus.
Yeah.
A big leap. What came after that in CERN's antimatter adventures?
In 1982, they built the low-energy antiproton ring, LEAR. This facility led to 3 major advancements: the creation of antiprotonic atoms, the creation of antihydrogen atoms, and the ability to trap antiprotons using electromagnetism.
Okay, let's break that down. Antiprotonic atoms, what are those?
Basically, imagine an atom where an antiproton replaces an electron orbiting the nucleus. This allows us to study antiprotons with incredible precision.
It's like a hybrid atom, part matter and part antimatter.
Fascinating. And then you mentioned creating antihydrogen atoms. That sounds like something straight out of Star Trek.
It does. They combined antiprotons with positrons, the antimatter version of electrons, and created entire antihydrogen atoms. It was a crucial step toward understanding the fundamental symmetries between matter and antimatter.
Building antimatter piece by piece, from antiparticles to entire atoms. That's incredible. And what about trapping these antiprotons? Why was that so important?
Before trapping, antimatter would annihilate almost instantly upon contact with matter, making it extremely hard to study. But with electromagnetic traps, they could suspend antiprotons in a magnetic field, preventing them from touching matter and allowing for longer studies.
Like a magnetic cage for something that would otherwise disappear in a flash. So these advancements really opened up the field of antimatter research. Absolutely. They paved the way for even more precise experiments. In 1997, CERN created the antiproton decelerator, AD, later enhanced by the extra low energy antiproton ring, LNA. These facilities provide the world's only low energy antiproton beam, enabling a whole new generation of experiments.
They went from creating and trapping antimatter to having a dedicated antimatter factory. Amazing. What are some of the standout results from these newer experiments?
For instance, the ACSI experiment measured the antiproton to electron mass ratio with incredible precision, 0.8 by 10 to 9. This confirms, to a high degree, that antiprotons and electrons have the same mass ratio as their matter counterparts.
Wow, that's mind-boggling precision. What other groundbreaking results have come out of CERN's antimatter program?
The LPA experiment has been doing some fascinating work with antihydrogen. They've made spectroscopic measurements of antihydrogen, achieving a precision of 2 by 1012, and again, they found no difference from hydrogen.
Spectroscopic measurements, meaning they're analyzing the light emitted by antihydrogen.
Exactly. And these measurements help us test one of the most fundamental symmetries in physics, CPT symmetry. This symmetry suggests that if you flip the charge, parity, and time of a particle, its behavior should remain the same. So far, antimatter seems to be playing by the rules.
So studying antimatter is helping us test some of the most fundamental laws of physics. What's next for antimatter research at CERN? What mysteries are they still working on?
There are ongoing efforts to understand how antimatter interacts with gravity. Does it fall up or down? Does it experience gravity the same way as matter? Experiments like BASE and ALPHA are trying to answer these fundamental questions.
Antimatter and gravity. It's like something out of science fiction. What about the future? What are the big goals for antimatter research at CERN?
The dream is to create even more complex antimatter systems, maybe even antimatter molecules or antimatter nuclei with multiple antiprotons and antineutrons. And there's a push to expand the network of antimatter experiments beyond CERN, transporting antiprotons to other facilities to diversify the research.
From creating the first anti-atoms to potentially building complex antimatter structures. CERN is pushing the boundaries. But CERN's ambitions don't stop at antimatter, do they? They've also recreated the conditions that existed just microseconds after the Big Bang.
That's right, and that's where our next milestone takes us, the discovery of the quark-gluon plasma, a state of matter that existed in the very first moments after the Big Bang.
Now that sounds like a story for the ages. We're talking about conditions so extreme they defy our everyday experience. What kind of environment are we talking about?
Imagine a state of matter so hot and dense that protons and neutrons melt away, leaving behind a sea of freely roaming quarks and gluons. That's the quark-gluon plasma, or QGP, and it existed in the very first moments after the Big Bang.
Quarks and gluons roaming free. I thought they were always trapped inside protons and neutrons.
They are, under normal conditions. The strong force which binds quarks and gluons together is incredibly strong, preventing their isolation. We call this color confinement. But at extremely high temperatures and densities, this confinement breaks down, setting the quarks and gluons free.
So it's like unlocking a fundamental force, creating a state of matter that hasn't existed since the dawn of time. How did they manage to do that?
CERN achieved this incredible feat using ultra-relativistic heavy ion collisions. They smash heavy nuclei, like lead, into each other at nearly the speed of light. The energy released in these collisions is unimaginable, momentarily recreating the temperatures and densities that existed just microseconds after the Big Bang.
So instead of protons and antiprotons, they're using entire atoms as projectiles. And what happens when these heavy ions collide?
The energy density is off the charts, millions of times greater than anything we can create in a lab. A tiny fireball forms, reaching temperatures exceeding trillions of degrees Celsius. It's like compressing the entire history of the universe into a single fleeting moment.
It's incredible. But how do they know they actually created this quark-gluon plasma? What's the evidence?
There are a few key signatures that physicists look for. One is the enhanced production of strange hadrons, which are particles containing strange quarks, heavier than the up and down quarks found in ordinary matter. In the intense heat of the quark-gluon plasma, strange quarks are produced more easily.
Okay, so more heavier particles popping into existence than expected. What other evidence supports the QGP hypothesis?
Another key observation is the suppression of JP-psi mesons. These are particles made of a charm quark and an anti-charm quark. In a QGP, the strong force is weakened, making it harder for these charm-anti-charm pairs to bind together.
So they had two independent pieces of evidence, both pointing to the creation of a new state of matter. And did the scientific community accept these findings?
After years of careful analysis and scrutiny, the consensus was clear. The quark-gluon plasma had been discovered. The announcement came in 2000, a major milestone in understanding the early universe.
That's incredible, but the story doesn't end there, right? What happened after the discovery?
The discovery of the QGP opened a whole new field of research. Physicists wanted to know more about its properties: temperature, density, viscosity, and how it transitions back into ordinary matter. This led to new experiments at the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Laboratory in the US, and also at CERN's Large Hadron Collider.
So from the SPS to RHIC and the LHC, the quest to understand the QGP has continued to push the limits of experimental physics. What new insights have these newer experiments revealed?
One surprising finding was that the QGP isn't quite the free-flowing soup of quarks and gluons that was initially imagined. Even in this extreme environment, quarks and gluons still interact strongly with each other.
So they're not completely free, but they're not bound together in the usual way either. It's a very strange state of matter.
It is, and this strong interaction within the QGP means it behaves more like a near-perfect fluid with incredibly low viscosity, like a liquid that flows with almost no resistance.
A cosmic superfluid. And what are the implications of this discovery?
This near-perfect fluid behavior gives us fascinating insights into the dynamics of the early universe and the nature of the strong force. It's like watching a replay of the universe's first moments, seeing how this primordial soup of quarks and gluons evolved into the structured cosmos we see today.
So by smashing heavy nuclei together, we're not only recreating the early universe, but also uncovering unexpected properties of matter under extreme conditions. What a testament to human curiosity and ingenuity.
Absolutely. And this journey of discovery is far from over. Scientists are still working to understand the complexities of the QGP, hoping to uncover more secrets about the early universe and the forces that govern our reality.
But perhaps the most sought-after prize in particle physics, the one that's captured the imagination of generations of scientists, is the Higgs boson. Let's move on to this final milestone, the discovery that sent shockwaves through the scientific world.
Yes, the Higgs boson. The God particle, the key to understanding mass. This is where things get really interesting. The story of the Higgs boson starts with a puzzle, a mystery that had physicists scratching their heads for decades. The mystery of mass. Back in the 1960s, physicists were struggling to make sense of the theory of weak interactions with the concept of gauge symmetry.
Okay, I'm sensing we're about to get into some pretty deep physics here. Can you break it down for those of us who haven't spent years studying theoretical physics?
Imagine a world where certain forces, like the weak force, which causes things like radioactive decay, require their force-carrying particles to have mass. But the prevailing theory of the time, based on this thing called gauge symmetry, insisted that these particles should be massless, just like the photon, which carries the electromagnetic force. It was a real head-scratcher.
So like trying to fit a square peg in a round hole, something had to give. What was the solution to this theoretical impasse?
The Brout-Englert-Higgs mechanism, or BEH mechanism for short. This brilliant idea, proposed independently by several physicists in 1964, introduced a new concept: a scalar field that permeates all of space. This field, now known as the Higgs field, interacts with particles, and through this interaction, particles acquire mass.
A scalar field. I'm picturing a kind of invisible fog that's everywhere, even in the vacuum of space. And particles moving through this fog experience resistance, which we perceive as mass.
That's a good analogy. The BEH mechanism revolutionized our understanding of mass, resolving the conflict between the theory of weak interactions and gauge symmetry. It allowed the W and Z bosons to have mass, explaining their short-range interactions. But there was a catch. This BEH mechanism predicted the existence of a new particle, the Higgs boson.
So the Higgs boson is like a ripple in this cosmic fog, a manifestation of the Higgs field itself. And finding this particle would be proof that this Higgs field actually exists.
Exactly. And the discovery of the W and Z bosons at CERN only intensified the search for the Higgs boson. It was the missing piece of the puzzle, the final confirmation of the BEH mechanism and the standard model. The hunt was on.
So where did they start looking for this elusive particle? Was it another game of cosmic hide-and-seek?
It was a search that spanned decades and involved multiple accelerators and experiments. CERN's LEP collider helped narrow down the possible mass range of the Higgs boson. Fermilab's Tevatron, a powerful proton-antiproton collider, also joined the hunt, further constraining the Higgs boson's hiding place.
A global effort to find this missing piece of the puzzle. Did anyone ever doubt that it existed?
There were moments of doubt, of course, particularly among younger scientists who hadn't seen the evolution of the theory and the growing evidence. But deep down, there was a sense that the Higgs boson had to be out there, somewhere, waiting to be discovered.
It's understandable to be skeptical when dealing with something as fundamental as the origin of mass, but I'm guessing the skepticism didn't last long.
Not at all. In July 2012, the ATLS and CMS experiments at CERN's Large Hadron Collider, or LHC, made history. They announced the discovery of a new particle that matched the predicted properties of the Higgs boson. It was a moment of pure joy for physicists worldwide, the culmination of decades of effort and a triumph for international collaboration.
Wow. After decades of searching, they finally found it. A historic moment for science. What were the key ingredients that made this discovery possible?
It took the immense power of the LHC, the most powerful particle accelerator ever built, to produce the Higgs boson in sufficient numbers. And then the incredible ATLS and CMS detectors, technological marvels in their own right, sifted through the enormous amounts of data and pinpointed the Higgs boson's signature.
Brute force, an incredible finesse, a winning combination. And this discovery must have earned someone a Nobel Prize, right?
It did. Peter Higgs and Francois Englert shared the Nobel Prize in Physics in 2013 for their theoretical contributions to the BEH mechanism, a well-deserved recognition for their groundbreaking work.
So the Higgs boson has been found, the standard model is complete, and we finally understand the origin of mass. Is that the end of the story?
Not even close. The discovery of the Higgs boson is just the beginning of a whole new chapter. Now, scientists are studying its properties in detail, trying to understand its interactions with other particles and its role in the early universe. They're hoping it might even provide clues about physics beyond the standard model.
So the Higgs boson is a portal to new frontiers in physics. What are some of the questions that scientists are now trying to answer?
One of the big mysteries is how the Higgs boson interacts with itself. Measuring this self-interaction could provide insights into the details of electroweak symmetry breaking, the process that gives particles their mass. There's also a lot of interest in the Higgs boson's potential connection to dark matter.
Dark matter. Now we're really going deep into the unknown. How could the Higgs boson be related to dark matter?
Some theories propose that the Higgs boson could be a bridge between ordinary matter and dark matter, mediating interactions between these two seemingly separate realms. It's a fascinating idea that could potentially revolutionize our understanding of the universe.
So the Higgs boson might not only be the key to understanding mass, but also a window into the dark sector of the universe. Is CERN continuing to investigate this connection?
Absolutely. CERN is at the forefront of this exploration, using the LHC to search for signs of dark matter particles and to study the Higgs boson with ever-increasing precision. They're pushing the boundaries of what we know about the universe, looking for new physics and trying to answer some of the biggest questions in science.
It's been an incredible journey through CERN's 7 physics milestones, a testament to human curiosity, ingenuity, and the power of international collaboration.
It truly has. From confirming the standard model to hinting at its limitations, from the mysteries of antimatter to recreating the conditions of the early universe, CERN has consistently pushed the boundaries of human knowledge.
And the best part is, this journey of discovery is far from over. As CERN continues to upgrade its facilities and develop new technologies, who knows what groundbreaking discoveries await us in the years to come.
I completely agree. The future of CERN is incredibly exciting. They're always pushing the limits, and with upcoming upgrades like the high luminosity LHC and the potential for a future circular collider, the possibilities are endless.
More collisions, more data, a new frontier of exploration. The adventure is just beginning.
Exactly. And what makes CERN so inspiring is that it's a place where human curiosity and ingenuity come together to push the boundaries of knowledge and explore the deepest mysteries of the universe.
Well said. On that note of cosmic optimism, we've reached the end of our deep dive into CERN's 7 physics milestones. It's been a remarkable journey, and I hope you've enjoyed it as much as we have.
It's been a pleasure sharing these incredible stories with you. And if your curiosity is still burning, we have tons of resources and further reading materials on our website. So keep exploring, keep asking questions, and who knows what amazing discoveries await us in the vast universe.
Thanks for joining us on the deep dive.
It really is. And it's not just about those big splashy discoveries. It's also about all the smaller breakthroughs along the way, the incremental steps that ultimately lead to those big leaps in understanding. It's like building a pyramid, right?
Yeah.
Each stone, no matter how small, is essential to the whole structure.
So true. Each experiment, each measurement, each analysis adds to our understanding. bringing us closer to understanding the universe and how we fit into it. And with CERN pushing the boundaries, who knows what we'll uncover in the years to come. But we got so excited about the Higgs boson, we almost skipped over another milestone, recreating the conditions of the early universe.
Ah, yes. The quark-gluon plasma. We basically time traveled back to the very first moments after the Big Bang.
Talk about mind-blowing.
Right. And it all started with a simple question. What happens to matter in extreme conditions, like the early universe? Physicists had this idea that under intense heat and pressure, even protons and neutrons would melt away.
Melt away.
Yeah, their constituent particles, quarks and gluons, would be set free.
Wow. So those particles we thought were indivisible, they're actually made of even smaller parts.
Exactly. And under these extreme conditions, those smaller parts, the quarks and gluons, they can roam free. It's called the quark-gluon plasma, or QGP for short. A state of matter that hasn't existed naturally since the universe was a tiny fraction of a second old.
It's like a primordial soup.
A primordial soup of quarks and gluons.
And how did they recreate this primordial soup? Was it another one of their collider experiments?
You got it. Heavy ion collisions. Imagine smashing lead nuclei, those heavy atoms, into each other at nearly the speed of light.
Instead of individual protons, they're using entire atoms as their bullets.
It's like a miniature Big Bang, releasing a tremendous amount of energy. For a fleeting moment, a tiny fireball forms, and the temperature, trillions of degrees Celsius.
Okay, back up. Trillions of degrees.
Trillions. It's hard to even comprehend.
Right. It sounds like a glimpse into the universe's very first moments. But how did they know they actually created this quark-gluon plasma? What did they see?
It's tricky because it only exists for a fraction of a second, but they look for specific signs. One is enhanced production of strange particles. These particles contain strange quarks, which are heavier than the up and down quarks we see in normal matter. And in the heat of the quark-gluon plasma, those strange quarks, they pop up way more often.
Okay, so they're seeing more heavy particles than they expected. Is that enough to prove they created the QGP?
There's another sign, the suppression of certain mesons. Mesons are made of a quark and an antiquark. But in the quark-gluon plasma, the strong force that usually binds them is weakened, so those mesons have a harder time forming.
It's like the plasma is changing the rules of the game for these particles.
Exactly. And these observations, along with many others, convinced scientists that the quark-gluon plasma was real. In the year 2000, they officially announced its discovery, a huge step in understanding the early universe.
So they recreated a state of matter that hasn't existed since the universe was a baby. It's amazing what we can learn by smashing things together.
It is. But the discovery was just the start. They wanted to learn more. The temperature, density, how it flows, how it transitions back into ordinary matter. This sparked new research at RHIC, the relativistic heavy ion collider in the US, and of course at CERN with the Large Hadron Collider.
So the quest to understand this primordial soup has continued. What new things have they discovered?
One of the most surprising findings is that the quark-gluon plasma behaves almost like a perfect fluid, with incredibly low viscosity.
So it flows really easily.
Almost without any resistance. Kind of like a cosmic superfluid. This discovery has huge implications for our understanding of the early universe.
It's like watching a cosmic replay, seeing how this soup of quarks and gluons transformed into the stars and galaxies we see today.
It's mind-blowing, and this near-perfect fluid behavior, it also teaches us about the strong force itself. We're probing the very fabric of reality, seeing how those fundamental building blocks behave in extreme conditions.
So by recreating the Big Bang, we're learning about the universe at its smallest scales. What a journey this has been. From the first particle accelerator to the Higgs boson to the quark-gluon plasma, CERN has truly changed how we understand the universe.
It has been an incredible ride, hasn't it? A testament to human curiosity, to our drive to explore the unknown.
And this journey is far from over, right? With new upgrades and technologies being developed, who knows what amazing discoveries await us in the future?
I can't wait to see what they find next. The future of particle physics is bright, and CERN is leading the charge.
Well, on that note of cosmic optimism, I think we've reached the end of our deep dive into CERN's 7 physics milestones. It's been a true pleasure exploring these incredible discoveries with you.
A pleasure indeed. And if you're yearning for more, we've got tons of resources and reading material on our website, so keep exploring and never stop asking those big questions.
Thanks for joining us on the deep dive.